Okay, welcome everyone. Thanks for coming to, this is the week 5 webinar for the statistics class. And let me share my desktop and we'll talk about what we're doing. Okay, so here is the plan of the day. I will, as always, start out with any questions you might have. And then I'll get into sampling distributions. That turns out to be really important when it comes to this class. We're going to be using what we're doing today, the rest of the entire quarter. So very important to, pay attention and, ask questions when you have them. If there's something you don't quite get it, very important. We'll get into unbiased and biased estimators. We'll get into the central limit theorem for means, the central limit theorem for proportions, and the central limit theorem for sums. So that is the plan. I want to remind you that something really important and kind of large is coming up that's due on Sunday, but really the draft is due in a couple days. And what is that? Hoping you all know. Yeah, the project. So I want to really emphasize how important it is to not wait until the last minute to get this project going and done. So the hope is by Wednesday, you have a full draft of what you feel is a good project. Then you can email it to me. Then I will look at it. It might take a day because if you're all sending one, it's typically they're like 8 to 15 pages long. So it's a lot of pages for me to read. And then I'll give you lots and lots of advice on how to improve so that you can get a really good grade. If you wait until after Thursday at 8 in the morning, then I don't look at drafts. So the draft has to be sent. I like to reward people for getting things done early. So that's your reward for getting things done early. It's kind of like extra credit. So I did get a question about extra credit. That's basically extra credit is you send it to me and then I'll tell you how to improve your grade. Usually grades improve by at least 10% from draft to regular paper. So that's just a big note. And then if you look at it and you don't understand something that I've explained, then you should post on the project discussion board what your question is. Also, Braulio is around to help out a lot, right, Braulio? And I'm in office hours. So definitely take advantage of all the help you have. Okay, if you don't, then it's pretty hard to be on your own. You want to get the help you need. So very important to make that work for you. Okay, the project, I consider the project the most important part of the entire course because that's when you're really learning reality of statistics instead of theory of statistics. So anyway, that's a plan. So let me ask you any questions you might have about anything. This is a great time to ask. Any questions? How long does the project have to be? There's not, I purposely don't say it has to be over a certain number of pages because I found if I did that, then people just like type bigger and put a bunch of nonsense in. But typical good projects are usually 8 to 15 pages. And I want to mention and remind you, remember, I did give you a full, pretty like a half an hour or so explaining the project one. So it can't hurt to go back to that. I want to remind you a couple things. One is you are required to take the spreadsheet from your Google Sheets that you put your data in and make sure the columns that have your statistics are copied and pasted into your project. And the other thing is when you submit your project and not the rough draft, but the true, your project that you're submitting as your final project, a couple things, make sure all of your names are on it. So for, the 2 of you or 3 of you, make sure that your names are on the project. And by the way, you have to have a partner or two. You can't work up by yourself. It's a major penalty if you work by yourself. So make sure your names are on it, and only one person submits on Canvas. So there's a place to submit on Canvas. One of the project partners submits, and then you all get the same grade. So hopefully that answered the question. Again, I answered more than how long does it have to be. If you only have a page or 2 or 3, it is not long enough. That's a guarantee. It's, typically it's several pages. Because there's no way you can fit everything you need on a couple pages. Any other questions? Good question. Really good question. As in, do you all, as in everyone in your group? Yeah, just one person. Best is just one person submit the project. I mean, not submit, sorry, email me the project, and have all 3 of your names on it, or both your names on it. And then make sure that when you get my feedback, I'll email you back with feedback, then forward my email to your partners. If that makes sense. So that's my best suggestion. Yeah, definitely don't submit multiple versions, and only read one rough draft. So if you send me a draft, I gave you lots of feedback. Don't send me another draft. Probably you'll look maybe, but again, if you keep sending the drafts, I don't have the time to look at it all. So that's just a note. Okay, and I don't have a lot on my calendar on Wednesday and Thursday, or even tomorrow, so I should be able to get back to you, within not that many hours. I do sleep though, so don't expect me to, if you send it at 10 at night, don't expect to get it by 2 in the morning, because that won't happen, because I'll be sleeping. Any other questions? Any other question? I want to mention something important that happened while I was grading your week 4 exam. I think many of you are not reading my comments that I put on your discussion post when I grade it, because most of you did not, on the last question, the one I read instead of the one that the computer grades, you're asked to do an expected value, and you were asked to give an interpretation of it. And if you didn't put the words many and likely and average and close to, so those key words I talked about, you lost points. And I mentioned that on the discussion assignment that you had to do on that. I also mentioned it at the webinar, and you guys still lost points. So pay attention, please. I don't want to take off points. Okay, it's the kind of thing that, I told you had to have those words in your interpretation of the expected value, and a lot of you didn't and lost points. So there's no need to lose those points. That makes sense. Okay. So if there's no other questions, let me talk about sampling distributions. And what's hard about that is the word sounds like some other stuff that we've already done, and it's not the same thing. So we've talked about distributions, we've talked about a sample, but sampling distributions are different. So I have a survey question for you to answer. And again, if you put in the chat box, it does not go on the video. I'll put the numbers in the video, but not your names. So don't feel bad if whatever you say. How many hours a week do you work? And I want to ask you that survey question. So I want you to put it in the chat box, and I'm going to start putting the numbers in. 28, 32, 35, 35. There's more of you here. There we go, 21. Anyone else? 20. What do we have here? Is that 3? Yes, that's probably enough. Okay, so that's how many hours a week that you work. So we just did a sample, and this sample is of size 6. Not a big sample size, but it's all we can get. Consider this like the sample of online statistics students, and there could be thousands of them, and we just grabbed some. but that's okay. We're going to consider this now. Let's consider this the population. It's the population of students who are on this Zoom today. So now the next thing I want you to do is I want you to randomly choose 3 of these data values. So we have 6 values, and I want you to choose 3 of them. And I want you to randomly choose the 3. You don't have to type in the chat box the 3. Just give you about 10 seconds to grab 3 randomly selected of these 6. Okay, so hopefully you all have 3 of these data values on a piece of paper or in your head, whatever it is, but it's important. I recommend paper actually, or typed in a computer is fine. Okay, so each of you have collected a sample from this population, very small population, but that's okay. And each of you have collected a sample. So from that sample, what I want you to do is I want you, let's just find the mean. Find the average of your 3 numbers, and let's see if you can put the average of those 3 numbers in the chat box. And maybe round to 1 decimal place is good enough, just in case you have a bunch of decimals. So why don't you take the mean? You could use the fancy calculator or add them up, divide by 3 is a lot easier. And put in the chat box what you get when you add your 3 numbers up and divide by 3. Can't be 76. You can't have a mean that's over 35. That's not possible. Maybe you forgot to divide by 3. Yeah, 23 can happen. $25 looks a lot better. All right, so what we've got is the means that you got were, let's look at what we got so far. We have 23, 25, 31.7. 28. Okay. You just want to join in? Don't see y'all jumping in. I know there's a few more of you, but maybe we'll look at these. Okay, so what we have now is we have a new data set. These numbers, 23, 25, 31.7, and 28, these are sample means. Okay, that's what you did. You found a sample mean with sample size 3.
Larry, there's a 29 in the chat.
Did I miss one? 29? Okay, thanks. Yep. Thanks. Okay. So we have a bunch of sample means. All right. Well, when you look at these, now we have a bunch of numbers, right? If you have a bunch of numbers, then you can look at this as your new data set. Is that clear? Okay. And by the way, there are a whole lot of different sample means that you can get, even out of a sample size of size 6, and you're just doing 3 different ones. There's actually pretty many. I won't get into the heavy math, but there's a way of calculating that. And it's a lot. Okay. Imagine instead of this example, imagine instead of how many hours did you work a week do you work, and I asked you guys, what if I asked everyone in America? I'd have, a population size of, hundreds of millions of people, and we could do maybe a sample size of 50, and we could look at all possible samples of size 50. There'd be like trillions of those, but that's fine. But it'd be a collection of numbers. And when you have a collection of numbers, what do we do in our stats class when you have a collection of numbers? What are the kind of things we find from that collection of numbers? Who remembers? What are the main things we end up finding when we have a collection of numbers? Remember? Kind of 2 big numbers There's a few, but the two most important. Z-score is when you have one number, actually. And we find the z-score for that one number. But you have a big data set. For example, when you did your survey on your project, you put your collection of numbers into the spreadsheet. And what important things did it give you? What were the two most important numbers it gave you? Very important for your project, by the way. I don't see everyone jumping in. When I say it, you'll say, of course. Okay, if you don't remember, how about the mean and the standard deviation? Aren't those the two most important numbers in our stats class? Okay, so we could take all the possible sample means, like we've got some of them, but we could take all possible ones and then find the mean of those possible numbers. We can find the standard deviation of those possible numbers. Okay, we could draw a histogram of those possible numbers. And we could look at the shape of the histogram and say, hey, does it look like a normal shape? Does it look like a uniform shape? What does it look like? Does that make sense? So what we call that kind of shape and the mean and standard deviation, all that stuff, is the distribution of the sample means. And we often call that the sampling distribution. Any questions on that idea? So here's some notation, and this can get a little confusing because it puts together notation we've already had. The population mean of all the possible sample means. Well, since it's a population mean, we use mu because mu is the population mean. But it's the mean of the sample means, so it's mu sub x bar because x bar is sample mean. And that's the notation we use for the population mean of all the sample means. Any questions on that? Any questions on the notation or what I'm talking about? This can get a little confusing. Okay, next, we can talk about the population standard deviation of all possible sample means. So that's a population standard deviation. We use sigma to talk about population standard deviation. And it's that deviation, or standard deviation, of all the x bars that you could possibly grab. Any questions on this idea? Very important, by the way. Then you might say, what is the distribution? What do you get? Any questions on this whole process? Okay. The sigma sub x bar that we just saw is also called the standard error. This because it's too long to say the standard deviation of all possible sample means. It's a lot easier to just say standard error. So that's the name they usually give it. Any questions on that? All right, so once we know that, now comes some important stuff. The sampling distribution. The sampling distribution for a statistic. So in this, usually we're going to be doing either means or proportions. For samples of size n, so our sample was of size 3. 3, by the way, is really tiny, but just for to make life easier, we just made it short. But normally you have bigger sample sizes, is the distribution of all possible sample statistics from samples of that size. So it's pretty abstract. As we go, we'll talk about real examples come up in all over the place. So what that tells us, and this is important, pretty much everything we do in statistics involves collecting a sample and looking at the data. And when you collect a sample and you look at the data, then your sample mean is going to be, if it's quantitative, your sample mean is, you can think of it as one of all the possible means. And you want to see kind of where does that belong? That's kind of what's going on in the big sampling distribution. So now a couple little definitions. By the way, I'm starting out with kind of definitions, and then we'll get into some important examples. A statistic is an unbiased estimator for a parameter if the mean of the sampling distribution for that statistic is equal to that parameter. So in particular, what we looked at was all the different sample means of sample size 3. If you take all the means of sample size 3 and look at the mean of those means, then that will be the population mean that you started with. And that means it's unbiased. Okay, so the sample mean is an unbiased estimator for the population mean. Okay, let me give you another example I'd like to bring. Let's suppose we asked 30 people. And we asked, how much do you weigh? And let's say you randomly selected 30 Americans. You're going to get 30 weights. Is that clear? And you looked at the range of your 30 weights that you got. And the range would be the heaviest minus the lightest. Is that a good estimate for the range of all for all Americans? What do you think? Yeah, it's a terrible estimate, because if you randomly selected 30 people, you are not going to get that huge, gigantic person. You're also not going to get that infant that was just born like way too early and is only like 1 pound. Okay, because the range is going to be really the difference between those two people. That's the range of the population. The range of your 30 people is going to be nowhere near that length, almost certainly. I mean, there's a small chance, but it's very unlikely for you to have a range from your 30 people you surveyed that is anywhere close to the range of the population. Okay, if you look at all the average ranges of size 30, that's going to be much smaller than the range of the whole America. So the range is a biased estimator for the population range, which means that if you take a sample, you're never going to use that range of that sample as a best guess for the range of the population. On the other hand, if you take a sample and you look at the mean of that sample, that will be your best guess for the mean of the population. It's not perfect, but it's a good guess. Any questions on that? Okay, the sample proportion is also an unbiased estimator for the population proportion. If you randomly selected 100 people and asked them, you know, something like, have you had COVID yet? Well, if you truly randomly selected 100 people, it's not that unlikely you're going to be close to the population proportion of those who've had COVID. Any questions on that? I'm not proving it, but hopefully you can trust me that it's true. Whereas a range is nowhere close to it. Okay, now comes the most important theorem of the entire course. So not the day, but for the entire class, and not just for the entire class. If you took 100 courses in statistics, I don't know if there's that many, but I've probably taken, 9 courses in statistics. And it is clearly the most important theorem of every course I've ever taken in statistics. And it's called the central limit theorem. And it says the following. This is very important. The sampling distribution for sample means from samples of size n has mu sub x bar equals mu. Another way of saying that is that the sample mean is an unbiased estimator of the population mean. On the other hand, sigma sub x bar is equal to sigma divided by the square root of n, where n is your sample size. Okay, so if you look at all possible sample means of sample size, let's say, 49, then the standard deviation of all possible sample means of sample size 49 will be the standard deviation of the population divided by the square root of 49. And if you don't know, the square root of 49 is 7. So that'd be sigma over 7, which is much smaller than sigma. Divided by 7 makes the number much smaller. Any questions on that idea? Okay, this right here, which I've highlighted, I'm pointing to, is really the most important formula there is in all of our class. And that is that sigma sub x bar is sigma over root n. And what that means, if you want your sigma sub x bar to be small, and remember, sigma sub x bar is small, then that means that your x bars are all going to be close to each other and close to mu. So if your n is large, then sigma over root n will be small because you've divided by root n. And if that's small, that means your sample is very likely to be close to the population mean. Your sample mean is likely to be close to the population mean. That is the whole point of getting a large sample size, is that way you have a reliable estimate. Okay, so number 2 is also very important. If the population's distribution is normal, or if the sample size is large, and in our class, our definition of large will be greater than 30. Where have you seen greater than 30 in this class? I've said it many times, but I told you you're going to have to wait until you hear why it's important. Now you're hearing. Where have you seen it? Where have we talked about a requirement of greater than 30? Yeah, project 1, right? You have to have over 30. That means a minimum of 31 people that you surveyed for project 1. Does that make sense? That's a requirement of project 1. And I did the over 30 because if you don't have over 30, you don't have very reliable data, because you can't use a normal distribution, which means you have no idea what distribution you have. But if you have a normal distribution, then the sampling distribution for the mean is also approximately normal. So if you have a large sample size, then the sampling distribution for the mean is approximately normal. Okay, again, that theorem, I'm not proving it, but hopefully you can trust me. All right, so now I'm going to have, in my opinion, it may not be yours, the most valuable piece of information that you're going to get in this entire course. Okay, and valuable means valuable for your life. Okay, now that could depend on what your career is going to be, but for most of you, this is going to be really valuable. And I'll explain how I've made it valuable. Okay, so I'm going to do a couple scenarios. The first one, if you put $10,000 into the bank, what's the probability that you're going to end up losing money after 1 year from that $10,000 that you put into a bank account that you're not touching, by the way, during that year? It's such an easy question. You should all know the answer. It's super easy. If you throw it, let's say, put in a Bank of America, put $10,000 into Bank of America, you put it into a savings account, you don't touch it. For a year, you come back a year later, what's the probability you're going to end up losing money? Yeah, 0. So the answer is 0. And let me write down P, that X is less than 0. So the amount of money you end up getting, or say your interest rate is negative, is equal to 0. So putting money into the bank is super safe. And by the way, I'm calling it 0 because it is FDIC insured. So the only way that it could happen is if like America like goes away and isn't America anymore, because even if the bank goes bankrupt, America gives you money back. I don't know if you know that the government gives you your money. So you cannot lose money basically. Okay, but here's the big problem. What's the mean interest rate? What do you think the interest will be if you put a 10,000 into the bank? Okay, so 0.01, so 1%. We'll call that 1%. Sounds good. So I'm going to go 1%. Okay, and again, it really depends on, what bank you might go to and stuff like that. But we're just going to make it life easy, 1%. So you have no chance of losing money, and you're going to make 1%. 1% of 10,000, by the way, is $100. Are you happy making $100? Okay, maybe you are, but I wouldn't be. All right, so now let me explain some more stuff. Okay, I'm going to throw in something in the news today. I always like to do that if I can. Do you recognize this website? Could do high yield savings. Yeah, but this is better. Do you recognize this website that we're looking at? Okay, if you don't, I'll tell you, there's the stock market. Okay, and if you look, I like it. Today was a really good day for me, by the way. I think I made $8,000 today. Can't hurt that, right? Okay, forget $100. All right, today the market went way up just today, over 1% in one day. Is that going to happen every day? No, definitely not. Okay, but today it happened. Okay, so more importantly, let's look at the stock market and see if you can guess. And I've done a little research on this, but maybe you have a guess. If you invest in the stock market, what do you think? What do you think the average rate of return is? What percent in over a year, by the way, over 1 year? Okay, 7% is one person. Anyone else ideas? I'm going to go over since the beginning of the century. We'll just call it that. Okay, let me tell you, it's about 9%. It's even better than 7%. All right, so if I invest in stock, does anyone have stock here? Okay, what stock do you have? You don't have to tell me, by the way, but if you want to, you can. Okay, and by the way, do you think I have stock? Given that I just told you. And the answer is yes, I've had stock for a very long time. Okay, and many different stocks, and I buy and sell a lot. And by the way, do you think I make pretty good money in the stock market, or do you think I lose money over the last, I've been doing it for about 40 years, by the way. Okay, I do some day trading. Not all the time, sometimes. I do some day trading. I also do other kind of trading. Okay, yeah, so because I understand statistics. Okay, I really understand. Hopefully you get that I understand statistics well, which means I know how to make money in the stock market. Okay, this year wasn't good though for anyone. Okay, so now we have a new one. Suppose that you put $10,000 into a randomly selected stock. Okay, just to let you know. Any guess? Maybe you'll guess because you know this stock. Any guess on what the last stock I bought was, which was not that long ago, a couple months ago, actually. No one wants to guess? You've all heard of this company. PayPal, good try. Yeah, Amazon. Okay, and it made money, by the way. I bought it though, like a real low. I'm really good at finding lows. It's all statistics. Okay, suppose you put $10,000 in randomly selected stock. Okay, mu is 0.09, 9%. And so let's make this 9%. And let's suppose sigma is 20%. Got it? All right. And let's assume that stock returns are normally distributed. It's not quite right, but we're going to have to do that for now. What's the probability that we'll end up losing money? So if it's normally distributed, how do you do this? It's not so hard. What the numbers we need are the low, the high, the mean, the standard deviation, and that's it. What's the low and the high for losing money? In fact, let's go right to it. I think it's easier. And I'm going to go here, and we assumed it was a normal distribution, a normal probability. What's the low for losing money? Not, yeah, negative 99999. Okay. What's the high for losing money? What's the highest amount you could make? Yeah, but if you get 99999, you didn't lose money. What's the boundary of losing money? In other words, less than what number is called a loss? It's really easy. See y'all jumping in? 0. Yeah. Anything under 0 is a loss. The mean was 9%. So I'm going to use 9. Don't deal with percentages. It's easier. And the standard deviation was 20. And I want the probability. And it looks like about, let's go to the nearest whole number percent, about 33% chance. So here, the probability that X is less than 0 is equal to 0.33. Okay, let's suppose that with this $10,000, if you lose money, you're gonna have to drop out of college because you can't afford it. Are you okay with having a 33% chance of losing money? You should all be able to answer this fast. I hope you all have the same answer. Not seeing you jump in. Are you okay with having a 33% chance of losing money if it's going to cause you to drop out of college? Yeah, you should all say no. I hope that having a 33% chance of having to drop out of college is not okay with you. Okay, so if you want to make sure that you don't have a high chance of losing money, this is a bad investment, even though it makes a lot more money on average than the bank. Is that clear? Is there a better investment than the bank where you don't have such a big chance of losing money? Any thoughts? Here's a hint. Any thoughts of a better investment? You just know a little about the stock market, right? But buying Amazon is the stock market. Any thoughts? Okay, so you may not know about this because this is not math even, it's business and investment strategies. Do you know what Dow is? Okay, yeah, a lot of you don't. What it is it's a selection of 30 different stocks that are kind of all over the place. So they're not completely independent, but they're pretty close to being independent. So there's 30 different stocks. So if you put your money into what's a Dow index fund or a mutual fund that's focused on Dow, then that company is going to buy 30 stocks in the Dow, the 30 stocks in the Dow, and your money now is distributed over 30 different stocks. Does that make sense? And the average of what happens to those 30 stocks is what you get. So if the average goes up, you make money. If the average goes down, you lose money. Is that clear? So now comes the next biggie. And that is, now let's suppose you invest 10,000 into the Dow Jones Index Fund. Okay. Which again, if you're doing like your retirement fund or like so many different things that you don't have to take out tomorrow. So it's kind of complicated to take out tomorrow. But if you're going to leave it for a couple of years, for example, then that's the way you want to go if you don't want to have a high chance of losing money. But what's the probability of losing money? We're going to assume Dow Jones is a representative sample, that the stocks are independent of each other, not perfect, but not that far away. The mu is 0.09 or 9%. Sigma is 20%. But we now are doing 30 stocks and we're taking an average of the 30. Any questions on that idea? So we're not looking at X anymore. We're looking at X bar because it's the average that you're invested in, not an individual stock. Any questions on that? All right. Well, 30, it's not over 30, but it's pretty close. So it's not that far from being normal. So now we're pretty certain it's pretty close to normal, not perfect though. Mean is going to be 9 because the central limit theorem says that the mean of the sampling distribution is the same as the mean, which is 9%. And the standard deviation will be sigma, which is 20% or 20, divided by the square root of the sample size, and the sample size is 30. So 20 over root 30. I popped that in my calculator. 20 over root 30 is about 3.65. And now we want to find out what's the probability that X bar, not X anymore, it's X bar, is less than 0. Any questions on that? All right, well now, everything is the same, but now we have 3.65 for our standard deviation, very different. So I can go in here, still gonna have negative 99999 for the low, still gonna have 0 for the high, still gonna have 9 for the mean, but the standard deviation is not 20, it's 3.65. So I can type in 3.65. And remember in the calculator, just ax it out, let it be blank, and hit calculate. Take a look. What's the chance of losing money now? Yeah, less than 1% chance. Okay, there's a less than 1% chance of losing money. Move the decimal 2 over, and it's actually 0.68%, if you want to call it percents. That's a big difference. So now what do you think about the idea of taking the $10,000 and instead of putting it into like a single stock, put it in the Dow Jones Index Fund? What do you think? Okay, it's much better. Okay, because now you can invest. I want to let you know we assumed there's an independence and it's not true. But for a long amount of time, you get independence. 1 year is not quite enough, just let you know that. But for several years, you're pretty darn good. Okay, so do you know what happens if you put money in the bank? Do you know what the bank does to it? Any guess? It uses some of it for loans. Do you know what it uses for the rest? Any guess? Puts it in the stock market. Yeah. Because if you're a sucker and you put all your money in the bank, then the bank takes advantage of you and puts it in the stock market and makes money. Okay, and you're helping them out, making money. Much better is, invest. Does that make sense? But again, you want to make sure it's diversified. You might have heard that. Diversified means that it's kind of independent of each other. That independence is important. And long term, you're pretty safe with any index fund. Any questions on that idea? Okay. All right, so that's all you need. Okay. By the way, if I wanted the standard error, if I wanted the standard error instead of, I'm not gonna do this one. I'm gonna do a different one. If I want the standard error to be half of this number, then instead of 30, how many would I have to do? If I wanted to decrease by a factor of 2, what do I have to do to the sample size? Any thoughts? So if I want to decrease by a factor of 2, I need to increase the sample size by a factor of 4 because it's under a square root, and the square root of 4 is 2. Any questions on that idea? That's how the math works. It's not that hard, but you have to know that that's how it works. Okay. Do you think we're only going to be using this for investments? Any thoughts? Yeah, definitely not. Because what the main thing we're going to be using this for, I like the investments because one thing is you'll make more money in your long run. And, if you do that, you always want to have some money in the bank for emergencies, but for big, if you have a lot of money, you shouldn't have it all in the bank. Just a note. Okay. And the biggest thing we're going to be using it for is looking at a sample to estimate the population. And what that tells you is what this whole sigma over root n idea thing, it tells you how good an estimate you have. So we're going to do lots and lots of examples throughout this whole class. Okay, next is the central limit theorem for proportion. Okay, and this is important also. So in terms of data, one of the main types of data you can have is quantitative. And then you're going to use central limit theorem for means typically. But another type is the yes-no question. There is no mu, there is no sigma when you have a yes-no question. You just have yeses and nos. What you have is you have a proportion. And we use the letter P for the population proportion. We use the letter P with a hat on top. Very hard to type, by the way. It's a sample proportion. By the way, if you have a, let's say your next quiz, and you want to put P hat, it's fine. I'm not going to take out points if you write P hat. Okay, I'll let you do that. That's fine. I don't require you to know how to do fancy math symbol stuff. But I do want you to understand that you say that as P hat. Got it? So that could be for discussion post. It could be for your exam word problems. That you should have P-H-A-T, because honestly, this is really hard to write it with this way. Okay. And here's the big theorem for the central limit theorem. So imagine so if you now ask a lot of people a yes-no question. So if you asked a question such as, have you ever had COVID? Okay, what are the possible answers to have you ever had COVID? Yeah, yes or no, and that's it. Okay, the yes-no question. Okay, on the other hand, if you asked, let's say 100 people, have you ever had COVID? Then you could look at the proportion of people who said yes, and that could be, say, 0.25 or 0.38. Okay, so the nice thing is when you're looking at sampling distributions, even for proportions, you're looking at quantitative numbers based on that sampling distribution. You could take the mean of the number you could take the mean or the proportion of yeses instead of just, is it yes or no? That's how you turn it into quantitative, is you take the proportion of yeses from a sample. And the population mean of all possible proportions of sample size n is equal to the population proportion. Okay, the next one is the population standard deviation of all possible sample proportions of size n is equal to this formula, the square root of p times q over n. P is the proportion of yes answers, q is the proportion of no answers, and n is the sample size, always. Anyone lost on what I just, on this right here? Very important formula. Okay, one thing that's very important to note, the n is in the denominator and under the square root. You see that? And if we look at the original central limit theorem, we had an n in the denominator under a square root. So the good news, if you increase your sample by a factor of 4, then you're going to decrease the standard error by a factor of 2, whether it's proportions or sample means. Any questions on that so far? Okay, then the next, if n times p, which is the predicted number of yes answers, and n times q, which is the predicted number of no answers, by the way, and if they're both larger than 5, then the sampling distribution is approximately normal, which is great because if it's approximately normal, then you can actually find it. Any questions on that so far? Okay, so this is very important. Okay, now I'm going to require you put something in the chat box. Remember, this is not posted on the YouTube or anything, but you need to put the following words in here. For a yes, no answer, I will not use the number 30 to decide if my sample size is too large, is large enough. For a yes, no, I'm going to type it too. Answer, I will not use the number 30 to see if the sample size is large enough. You must all put that in the chat box. There's a reason. You don't have to have 2 those. There we go. So everyone has to put it in. Okay, if you have a typo, I'm okay with that. So don't worry about that, but I want you to type it. Okay, why am I making you do this? Any guesses? Because you've just promised, by the way. What you put in the chat box means you promised. Should I tell you? The reason I'm making you do this is it's the #1 mistake students make when you're dealing with central limit theorem stuff, is this right here, is using the number 30 on a yes/no question. Okay, and it's 5 that we're comparing. And it's not the sample size of 5. It's the number of yes answers and the number of no answers. So let me give you an example. And this is a real life, completely relevant example. And that is a few years ago, the biggest and the most important of all studies when it came to doing a sample was done. Probably in the last decades. Anyone know what that most important thing was? what study it was? Anyone guess? I don't see y'all jumping in. Not climate change. Climate change is important, but that one's kind of very long-term important. Health related in particular, I told you it was just a couple years ago. Yes. COVID vaccination. Okay. They did a COVID vaccination. They couldn't give the vaccination to everyone in the world before they tried it on a smaller number of people. Okay. Do you think they used 31 people to see if the vaccination worked? What do you think? Yeah, definitely not. Remember, a few years ago, very few people had COVID. Okay. Yeah. So what they used actually, they did what's called a control study. Do you remember what a control study is? That happened in chapter 1. Don't you hate when I say that? Okay. If you don't remember, what they did is they grabbed a lot of people and they took half of them and gave them the vaccination. And the other half, they gave them a shot with nothing in it. Yeah, placebo. And then they watched to see how many got COVID. That's a yes, no question, by the way. Did you get COVID, right? And then they wanted to see if those who got the real shot, the treatment group, had a smaller proportion than the control group, the people that did not get, that got a fake shot. Okay. And NP, if you remember a few years ago, if you looked at 31 people, if they're vaccinated or not, probably nobody's going to get COVID. Okay. COVID was pretty rare a few years ago. Okay. And we're talking about like in a month time. Okay. Very few people get COVID over a month. Does that make sense? So anyone know how many people they used? Probably not, because you're not a statistician like I am. So you didn't like pay attention to the numbers like I do. They used 25,000 for the control group and 25,000 for the placebo and for the treatment group. 25,000. And the reason why they had to use that many is the proportion of people who were getting COVID was very small. And they had to make sure that they would expect more than 5 people to get COVID. Okay. And to make it really accurate, they need a lot more than 5, it turns out. But that's how big the sample was. And they needed that big a sample because it was very rare in those days to get COVID in a 30-day period. Okay. And by the way, do you think there was a difference between the people who got the placebo and got the treatment in terms of the proportion of got COVID? And the answer is yes, because if there wasn't a difference, then they would never have approved the vaccination. But there was a very, very big difference between the two. Just to let you know, that's how statistics is used. And it's really important that you understand all the different kind of like important pieces of stats. If you don't do stats, you could end up having a vaccination that kills like everyone. That'd be horrible, or maybe kills 20% of the people who get it. And you can't just give it to the world. So it's really important to do stats properly so that you don't have disasters happen. Okay. And it could be killing people, or it could be losing your money if it's stock market kind of stuff, all kinds of things. Okay. Any questions on that? Okay, let me give you another real example since someone guessed it. Do the majority of Americans want the government to spend federal money to increase the number of electric vehicle charging stations in the United States? What do you think? Okay, so I would guess yes. Is guessing yes enough to say that we should spend it if you were a politician? Yeah, of course not. Of course not. Okay. So instead, what Gallup did actually is they did a poll. They did a survey. Okay. And they used stratified sampling. So it's pretty, pretty good survey. And here's what they got. They surveyed 1,017 Americans, and 59% of them said yes. Any questions on that so far? Okay. And we want to say, do the majority of Americans want the government to spend federal money? All right, so here is a way to look at it. And here's what statisticians do. Here's what people do. They say so first thing, if it's not the majority, then what's the largest percent it could be? Anyone know? I always get 49%. 49.5% is also not the majority, by the way. Turns out the largest percent you could be and not be the majority is 50%. Because to be majority, you have to be more than 50%. And by the way, that doesn't mean 51. 50.00000001 is good enough. Okay, so if 50%, because that would not be the majority of Americans. And let me write all Americans. So now we're talking about the whole population. Want the spending. Okay, so it's only 50% instead of more than 50%. Then what is the probability that of a randomly selected (1,017) Americans at least 59% of them would say yes. Any questions on that? Okay, and the idea is if that is a very small probability, then we're going to say something's wrong, right? If it's only like, a 2% chance, you're going to say, it's probably fishy. What assumption did I make in that sentence? What assumption did I make? I don't see you jumping in, so let me write it down. Right here. I assume 50% of all Americans want the spending. Does that make sense? So the idea is that this probability is really small. We're going to say maybe something's wrong with that assumption. And I want to let you know, we're going to spend weeks on doing what I just said. So I'm going to give you this example, which is a big thing in 2 weeks and 3 weeks and 4 weeks and 5 weeks and 6 weeks and 7 weeks, basically the rest of the course after next week. So now what we need to do is we need to find the distribution. And let me write down the sampling distribution. Any questions on that so far? Oops. There it is. Okay, so to do that, I need it to be somewhat fancy, so I have to do math. And then we're going to say we want to find out what the probability that a sample proportion is going to have something. So that's going to be p hat tilde. And with Google, I believe it's been a while, but I believe there's a way of having it. Yep, there it is. So p hat. Okay, is it normal? Is the distribution normal for the sampling distribution? And what we need is we need to look at NP and NQ. Our P is 50% because that's our assumption. Our N is 1,017. If I go N times 0.5, you can put in your calculator, that one, this one I can do in my head easily though. And this one is 509.5. And by the way, that's NP. And NQ is equal to 1,017. By the way, if the probability of a yes answer is 50%, what's the probability of a no answer? Into this easy. Yeah, it's also 50%. So it turns out this won't be in every case, in every example, but if it's a 50%, this always works. It's also going to be 1,017 times 0.5, and that's also equal to 509.5, which are much bigger than 5. Do y'all agree? So that means I can write the letter N, and that's really important. Can't write the letter N, then you can't use the normal distribution. And that means our calculator doesn't work. And then we say that p hat is supposed to be equal to p for mu sub p hat. So that's 0.5 will be the mean. The standard deviation will be the square root of the fraction PQ over N, 0.5 times 0.5 over N, 1,017. Any questions at all on the distribution? Okay, we now have the mean, we have the standard deviation. And next is the low and the high. What's the low for this question? We want at least 59% of them to say yes. What's the low? Shouldn't be that hard. So what's the low? 59, but I'm going to write a 0.59. Make a decimal. And what's the high? What's the high? Yeah, high is 1, 100%. Highest you could be is 100% to be at least 59%. Can't be 200% yeses. So that means I can go in and I can do the low was 0.59. I can do the high was 1. The mean was 0.5. The standard deviation, I'm going to need to do some work. So that was the square root of 0.5 times 0.5 divided by, that was 1,017 is what. Notice the standard deviation is quite small. And I can copy that and paste it in. The P is what I want, and I hit calculate. What is this probability? Is the probability 4.7? Definitely not 4.7. What is it? Got to read it. That's the hint. Hint is look right. And I don't mean correct. I mean look in the direction to the right. Don't you divide it by 0.5 times 0.5? No. No. It's this E negative 9 that matters. And that E negative 9, you remember what to do when you see that? We've had it a few other times. That means that you have 8 zeros before the 4 in front of the decimal place. And I'll just do 4.7. So this probability (0 0.1, 2, 3, 4, 5, 6, 7, 8, 4.7). So what do you think? Do you think the majority of Americans think the government should put in, again, that was the question, should spend money to increase the number of electric vehicle charging stations? So do you think the majority think it's true that the majority think so? Don't like the number? No. The answer is yes, the majority do. Because if the majority don't, then the highest of a percent would be 50%, but there would be like such a small chance of that happening. It's not 50%, it's more than 50%. Do you see that? So that's how this is going to work. And we're going to spend many, many weeks on this kind of reasoning. If there's such a small chance that our assumption that it was 50%, that it not more than 50%, the assumption is 50%, then that means that this assumption is wrong and it must have been more than 50%. Do you see? Any questions on that? Okay, so we're gonna, again, if you don't 100% understand it now, that's okay. But if you don't 100% understand it in the next couple of weeks, that's not okay. Because we're gonna be doing it over and over and over and over again. This idea. Any questions on the central limit theorem for proportions? The big theorem. Okay, so if there's no questions on that, let's move to the next one. And the next one, actually, I don't need to spend much time on it. It doesn't happen as much, but it happens once in a while. And that is occasionally, instead of a mean, you want a sum. And another word for sum is total. Can you think of a situation you might care more about the total than the mean? And there's lots, by the way, not just one. Yeah, money if you are in business. So if you're in business, you care more about the total that you made for the day, not the average amount of money everyone spent. Does that make sense? So there are situations, and that's one example. There's a lot of other examples too. Okay, climate change is another one. we care much more about the total CO2 emissions that are made on Earth than the average amount of CO2 per person, because it's the total that's going to change the climate, right? That's the number that you care more about than the average per person. That makes sense? And there's lots and lots of other examples where total is helpful. But the mean will be more often, but occasionally we'll see total. So for the sampling distribution for the total, then the first thing, does anyone recognize that symbol right there? You might have seen it in a math class, or maybe you speak Greek, but you might have seen it in a math class. I don't think I've ever had a student that spoke Greek. Yeah, it means a sum of all, okay? So it's another word for total or sum. So, and unfortunately, it's sigma, but it's capital sigma. So this capital sigma right here, this is lowercase sigma. Just like in English, we have capital and lowercase letters that look different. So in Greek, they do too. So this is the mean of all possible totals of a certain sample size is going to be equal to the sample size times the population mean. And the standard deviation of all possible totals of samples of size n is going to be the standard deviation of the population times the square root of n. So instead of divided by it, it's times. And then it turns out for the normality thing for central limit, it's exactly the same as the central limit theorem for means. If the population's distribution is normal to start with, or if the sample size is larger than 30, then the sampling distribution for the sum is also normal. It should be the sum is also normal. Okay, so we're back to over 30, by the way. Just to confuse you, I guess. I don't know. Okay, the way you write it in symbols is your sum, this capital sigma thing, tilde, capital N, and then you go n mu, comma, sigma times root n. So here's an example. Okay, and it's a money example. I think that's the most common for totals. Is suppose the average customer at a restaurant spends $33.23. And the standard deviation is $9.22. If 65 customers eat at a restaurant today, okay, and we're going to assume that they're kind of randomly selected customers, what is the probability that the total revenue for the restaurant will be less than $2,000? Okay, what is the first quartile for the total revenue for a day? Any questions on the question? All right, so the first thing we do is let's get to the sampling distribution. I'm going to copy and paste as the easiest way of doing it and change things. What's n? Yeah, n is 65. And by the way, because n is 65, I have a normal distribution because that's bigger than 30. What's mu? Not 922. Yeah, 33.23. It's the average is mu. What's sigma? There's your 922. 9.22 times the square root of n, and n again is 65. Any questions so far? Okay, for the first question here, We need the low and the high. Here's a hint. What's the low? You could say 99999, you'll get away with it. But since this is a real life problem, the low is actually 0. You can't have revenue less than 0. But we'll use -999 because it'll work. How many nines you want. What's the high? Yeah, that's the 2000. And now we're ready. Pop it in. The low was -99999. The high was 2000. The mean was 65 times 33.23. Which is this wonderful number, 2159.95. And the standard deviation was 9.22 times the square root of 65. Whoops, I lost it. There we go. Times the square root of 65. And that's 74.33 and a bunch of stuff. So I'll copy and paste it in. P is what we want to find out. And I hit calculate. So is that a high probability or a low probability? Yeah, it's a low probability. Around, 1.6% chance. 0.0157. Have I lost anyone? I do want to warn you that watching me doing it is a lot easier than doing it yourself. Do you agree? Yeah, so that's a warning. So you definitely want to practice, but watching an example helps. Watch it a few times and then try one similar and see how you do. Okay, what is the first quartile for the total revenue for the day? All right, remember how to do first quartile questions. Remember how to do a first quartile? Yeah, now we know P is 0.25. What do we leave blank? Yeah, the high is the one's left blank. The low really is -99999. And I calculate it, and there's your first quartile. I'll go 2 decimal places because it's money. Dollars and cents. So Q1 is equal to $2,109.81. Any questions on that? Any questions? Okay, so that's an example with sums. So now, since I've done all the main things that I promised I was going to do, is the secret word. And it's not even a word, it's an abbreviation. Capitalized, by the way. What does CLT stand for? It's not cheese, lettuce, and tomatoes, by the way. Yeah, central limit theorem. Okay. And a lot of people just write CLT because it's a lot easier to just type those letters. And by the way, if you're asked a question for the quiz, you can write by CLT, and that's fine. Okay. And that if you're using central limit theorem. So that's the secret word for the day is CLT. So I just want to recap the big theorem, the central limit for sums. The mean is n times mu. The standard deviation of all the possible sample sums is sigma times the square root of n. For proportions, mu sub p hat, the mean of all possible sample proportions, is just the population proportion. And the standard deviation of all sample proportions of size n is the square root of pq over n, where p is a proportion of yeses, q is a proportion of no's, n is a sample size. Okay, and really important, you want to find out if you have a large enough sample size to use the normal distribution, then you got to calculate NP, see if that's bigger than 5. You got to calculate NQ, see if that's bigger than 5. And if they both are, then the sampling distribution is approximately normal. And by the way, there is no plan B. Okay, you cannot use the normal distribution, period, ever, if you don't have NP and NQ greater than 5. You're not even close. Any thoughts? There is actually another distribution you could use. Any thoughts of the other distribution? Hint is it's yes, no stuff. I know it's been a while, a couple weeks. Now, see y'all jumping in, the binomial distribution. Okay, but the normal distribution is easier to use, the calculator is simpler, and it's what everyone uses. So if you can have NP and Q greater than 5, it's better to use the normal distribution. And it's close enough. Binomial is perfect, though. Okay, and then the central limit theorem for means, which is kind of the most important, that is mu sub x bar, the population mean of all possible sample means of size n, is just the population mean of your population to start with. And sigma sub x bar, the population standard deviation of all possible sample means, is the population standard deviation of your original stuff divided by the square root of the sample size. And the important thing is, if you want a smaller standard error, you need to make n bigger. Okay, and greater than 30 is what you need to be able to use the normal distribution, or if the original distribution is normal, which is rare. And that's the central limit theorem. And I'm looking at my watch. I always try to end around 7:30. And any guess on what time it is? The hint is if it takes you like 30 seconds or so, then I'm happier. Because right now it's 7:29 and a half. So I think I'm going to stop the share and stop the recording.